In the previous videos, we have learned about general orthogonal coordinates and applied them to cylindrical coordinates. Here, we will apply what we have learned to spherical coordinates. This first video will introduce the transforms for spherical coordinates. The next video will be about integrals, and the final video will be about derivatives. Let's start by introducing spherical coordinates. Start by drawing the position vector r. We know from Cartesian coordinates that the position vector is given by the coordinates x, y, and z. Its length is given by the Pythagorean theorem. Now, we are going to introduce the angle between the z-axis and the position vector as theta. This means that we can divide the vector r into a vertical part given by r cosine theta and the horizontal part given by r sin theta. The horizontal part is the vector we called rp when we talked about cylindrical coordinates, or the radius from polar coordinates. The vertical part is just the z value. The theta value is given by arctan of rp over z. We can also write that rp is the length of the vector in the xy plane, or square root of x squared plus y squared. As rp isn't normally used for spherical coordinates, insert its expression instead. Also note that for negative z, where arctan gives a negative theta, you should add 180 degrees, or pi radians, to the angle. Next, we will introduce the angle phi as the angle between rp and the x-axis. This is the same phi as we have used in cylindrical coordinates. Therefore, we can use the same equations as for cylindrical coordinates and write that x component is rp cosine phi and the y component is rp sinus phi. We can also calculate phi just as we did in the previous video using arctan y over x. Remember to add pi if x is negative. As we don't want to use rp in spherical coordinates, replace it with r sinus theta. Now, we have a way of calculating x, y, and z using r, theta, and phi, and can insert it into the position vector. We should also discuss the limits to the values. R is the length of the position vector and should be larger or equal to 0. If you want to create the negative vector, simply replace theta with pi over 2 minus theta, and then add pi to the angle phi. Theta should be between 0 and pi. This is just a half circle. To get the other half, we add pi to the angle phi instead, and can then complete the other half of the circle. This also means that phi should be between 0 and 2 pi. With these limits, each value for r, phi, and theta will correspond to unique values for x, y, and z. However, there are a few exceptions to what I just said. If our point is on the z-axis, which means that x and y both are 0, all values for phi give the same point. Hence, we cannot calculate phi for points on the z-axis, as all values work, and we say that phi is indeterminate. At origin, we get a 0 vector for all values of theta and phi, Hence both are indeterminate. You should be aware of these when you convert values to spherical coordinates to avoid 0 over 0 for your arctan expressions. Moving to our next topic, which is unit vectors. Here, we will use the method we introduced for general orthogonal coordinates. In the general case, we used coordinates u1, u2, and u3. These will be r, theta, and phi here. The general formula states that unit vector ui hat is given by 1 over hi times the partial derivative of the position vector with respect to ui. Hi is the length of the partial derivative with respect to ui. For the first coordinate r, we start by taking a small step in this coordinate, which will give the direction. Next, set up the expression for the partial derivative, which we can see is the difference between this new point and the base point we started from. To calculate it though, we can simply differentiate the r vector in the traditional way. We can note that this derivative is the same as dividing the position vector r with its length r. This gives the unit vector r hat, which can be inserted here. As we directly got the unit vector, the length is 1. Next is the partial derivative with respect to theta. Here we take a small step in theta value, which gives the following new point. The actual length of the step is the scaling factor h theta times delta theta. Let's calculate the partial derivative directly from the position vector. We also need to calculate the length of the partial derivative. We can place r outside the square root. Cosinus theta squared is a common factor. This is 1. And this is 1 again. And we get that the scaling factor h theta is r. If we look at the vector created by our small step in theta, we can also see that it varies linearly with r. To get the unit vector, normalize the partial derivative by dividing by its length r. We can now call the new unit vector theta hat. And we can divide by r. This is the final expression for the second unit vector theta hat. Continue with the third vector by taking a small step in phi. The length of this step is the scaling factor h phi times delta phi. Calculate the partial derivative. Next, we need the length of this partial derivative. We can place r sinus theta outside the square root. And this is 1. The length of this vector is the scaling factor h phi. By animating it, we can see that the vector for the small step varies with the radius. And also with the angle theta. Now, we normalize the partial derivative by dividing with its length. This is the unit vector phi hat. Divide by r sinus theta. And we get our last unit vector phi hat. Note that this is the same phi hat as we have in cylindrical coordinates. To ensure that we have a right-oriented coordinate system, the right-hand rule says that r hat cross theta hat is phi hat. We can now add the unit vectors to the illustration. All unit vectors stays the same if we change the value of r. R hat and theta hat change direction if we vary theta. Phi hat is constant here though. All three unit vectors change direction when we vary the value of phi. Now we know how to write the unit vectors r hat, phi hat and theta hat in terms of x hat, y hat and z hat. We also want to know to reverse this and get expressions for x hat, y hat and z hat. To do this, I will first show an alternative way of getting the unit vectors r hat, theta hat and phi hat. This time we will do it using only rotations. Let's start from the case where phi is 0 and theta also is 0. At this position, r hat is z hat, theta hat is x hat, and phi hat is y hat. As the first step, we give phi a value which rotates the unit vector around the z-axis. After this rotation, we basically have cylindrical coordinates, if we set theta hat as rp hat. Phi hat is also the same as we have in cylindrical coordinates. Next, we will rotate with angle theta around the phi hat axis. Using z hat and rp hat, this gives a similar rotation. We get expression for r hat and theta hat. However, we don't want to use rp hat in spherical coordinates. Insert expression for it instead. And distribute sinus theta. Repeat for theta hat. Insert rp hat. And distribute cosinus theta. Now we have derived all three unit vectors for spherical coordinates by only using rotations. The idea here is to reverse this process to get expressions for x hat, y hat and z hat. Start by reversing the theta rotation, which brings us back to cylindrical coordinates. We use the same rotation as before, but insert a negative angle minus theta. Cosinus minus theta is cosinus theta, and sinus minus theta is minus sinus theta. Apply the same here. Next, we reverse the initial rotation around the z-axis by rotating with minus phi. This will produce the same equations for rotation again. Apply the cosinus and sinus relationships for the negative angle again. And again. Then we insert expression for rp hat and distribute cosinus phi. Insert rp hat again and distribute sinus phi. This is how we can create x hat, y hat, and z hat in terms of r hat, theta hat, and phi hat. Next, we want a way of converting vectors between different unit vectors as well. Let us use the general way and use projections through the dot product. The VR component is v dot r hat. Insert both in terms of x hat, y hat, and z hat. And calculate the dot product. Note the similarities between the equation for r hat and the equation for VR. All we need to do is replace x hat with vx, y hat with vy, and so on. This pattern will work for all directions, and I will only type out the results for the remaining ones. These are the equations you need if you want to rewrite the vector from Cartesian to spherical coordinates. Or if you want to go in the opposite direction from spherical to Cartesian coordinates. This is the final expressions for how to convert between the two coordinate systems. Next up will be how to calculate integrals in spherical coordinates. Thank you.